So, hello friends, welcome back to the course on relativistic quantum mechanics or quantum mechanics in the relativistic regime. So, today so in the last two lectures we have finished one module which essentially is about revising what quantum mechanics, non ordinary quantum mechanics or non relativistic quantum mechanics entails. So, we talked about Heisenberg's matrix mechanics, then also about Schrodinger equation, then some potentials, and then we also talked about the vector spaces, the Hilbert space, and so on. So, essentially all the properties of of the quantum mechanics when all the systems we are studying are in the non relativistic regime. Today we will now start. So, those two lectures correspond to what I called as in my syllabus as module 1, and there will be a bunch of assignments assigned to that part essentially. Now, coming to I then slightly modified the structure of the syllabus a little bit compared to what was advertised. There will be a new version which will come out. So, which right now what I am doing is going to introduce, because since we have already revised the entire quantum mechanics, now it is the right time to ask the question what happened to systems which we are considering, which are essentially going to be in the relativistic regime. Are there such systems which are interesting, and if so what happens? So, this is the so today we will start outlining the issues in relativistic quantum mechanics essentially. That is the basic idea. So, what does non relativistic? So far all our studies, all the review we have done so far corresponds to systems or particles whose speed or velocity is much less than the speed of light. So, v is less than speed of light essentially. Okay, this double much less than the speed of light, where c is equal to the speed of light. Now, what we want to do is see how to construct, okay, how to construct quantum mechanics for particles where v is very close to c, v is very close to c. These are called relativistic systems. So, quantum mechanics is signified by the fundamental constant h cross. So, if things are in the quantum regime, you assume that all the observables which you calculate and all the properties of systems which you calculate will somehow have this fundamental constant h cross in their formula or in their calculations and so on. So, in the special theory of relativity case, in the relativistic case, mechanics, it is associated with the fundamental constant of nature, which is the speed of light in vacuum. Speed of light in vacuum, which is somewhat of this order, which you all know, essentially 3 into 10 power 8 meters per second essentially. So, this is a fundamental system, fundamental constant. So, all the mechanics which we study is associated with this particular constant. So, what you expect in relativistic quantum mechanics or quantum mechanics of particles in relativistic regime means that you would expect both H cross and C to appear in their observables essentially. So, both H cross and C will appear in the observables. So, that is the expectation we have. Now, before going further, let us try to revise, because we already revised the quantum mechanical picture, okay, we already revised the quantum mechanics completely. Let us try to revise what is the postulates of special theory of relativity and in doing so what we will try to do is introduce a notation which will be useful for us actually. Now, let me tell you that there will be later on what I will do is actually build a complete a separate module is designed only for to study what is called the Lorentz group and its representations, which we will do a bit later. But as of now we will just try to follow the general philosophy behind this entire course essentially, just to give you the physical picture. So, we will do a Lorentz group and its representation, Poincare group and its representation a bit later on. Okay. So, what is special theory of relativity, which was discovered by Einstein in the year 1905 while studying Lorentz transformation on electromagnetic fields. Special theory of relativity rests on two tenets or two postulates. So, what are the two postulates with the special theory of relativity rests on? All the physical laws, the first one is are the same in all inertial frames of reference. So, all the physical laws should hold true in inertial frames of reference, on all inertial frames of reference. In inertial frames of reference you can call them as something associated with the frame of reference of distant stars. Okay. Okay. Inertial frames essentially are a freely falling body, so on so essentially. So, these are inertial frames. So, so the physical laws should be the same in every inertial frame of reference. In every frame, whatever which you call as an inertial frame, that is just a nomenclature. Any frame, okay, you should have the physical. So, whatever so Newton's law should be same in every, whether we are sitting in the train or if we are standing still. Okay. So, wherever you are sitting, whatever you see, okay, it or whatever you observe should follow the Newton's laws essentially. So, Newton's laws should be the same in every frame of reference wherever you make the measurements essentially. Similarly, not only just Newton's laws, the electromagnetic laws and so on so, Maxwell's equations of motion, so on so. The second feature is the speed of light is a constant in speed of light in vacuum is a constant in all frames of reference. So, that means if you remember in the relativity and Galilean relativity or any other relativity, the velocity, okay, if you measure in one frame of reference and another frame of reference, the velocity can change. So, if you are moving in a if you are standing still, you measure the velocity of a body, but if you are also traveling on a motorbike or something, and then if you are measuring the velocity, then its velocity would be different essentially. So imagine that if you are there is a scooter which is going, and if you are standing here and you are measuring the velocity of the scooter, okay, then you can measure some velocity, some 30 kilometers per hour. But if you are measuring the same scooter's velocity traveling parallel to it, okay, on a scooter, okay, on another scooter, say for example, if you are also traveling at 30 kilometers per hour and traveling parallel to it like this, when you measure this velocity, its velocity is 0 essentially. So, depending upon the frame of reference, the velocity would vary. But the speed of light, it does not matter whether you are sitting, standing or running or traveling in an airplane or anything, or in any frame of reference, it is always a constant. The speed of light, if you measure it in a vacuum, it does not depend upon what is the frame of reference you are working on essentially. These two are the basic tenets or basic postulates of special theory of relativity. Now, we will not I will assume that most of the students know this special theory of relativity, but let me introduce you some notation which we will need throughout our work. This is the most important thing, and this notation is useful for rest of the entire course essentially. So, this is a very important notation which is we need to know. This is called the Einstein notation. So, the Einstein notation, so normally if we have a vector, so in 3 dimensions we have r bar, but special theory of relativity is given in x and t dimensions. So, it has 4 dimension where time is the 5th dimension, 4th dimension. So, to write it explicitly, x is equal to the 4 dimensions of special theory of relativity. If you write them in terms of some vector, you can write them as x, y, z and t. These are the components essentially of the vector. So, this is a position vector or it is a space time vector, because it contains both space and time. This is called a space time vector. So, ordinary R would contain x, y and z, whereas this one in 3 dimensions. So, there will be unit vectors associated with it, I, j, k and so on. So, whereas in special theory of relativity, because time also translates along with x, which also translates essentially, okay, time also translates. If you are moving, if there is a frame of reference moving with the speed very close to the speed of light, okay. So, along this thing essentially, if there is a frame moving this way, okay, if you have a frame S and if you have a frame S prime and this is moving with speed very close to the speed of light, okay. So, in this frame not only that there is a length which elongates essentially, and also there is a time length contraction, and there is also time dilations essentially. The time changes in the S prime frame, okay, if you are measuring it essentially. The space time vector is represented by, in the Einstein notation, in terms of something called x mu, which is called x mu. So, the mu is equal to 0, 1, 2, 3. Typically, if you write in this particular fashion, this means that your x mu is given in terms of t, x, y and z. Okay. This is a vector, okay, it is called x mu essentially. Now, there are various notations, what is something called a contravariant vector and what is a covariant vector essentially. Now, the point is that there is also, you can write another vector which is called contravariant vector, which can be written as minus t x y z. Okay, maybe I will start with the other way. Okay. So, this x mu is equal to t x y z and x mu is equal to minus t x y z. This is the index at the down, okay. This is an index at the down, and whereas this is an index on the upstate, okay. This is an upstairs index and this is a downstairs index essentially. Now, why do you need this? Why do you need this essentially? The way we need this is that because we want to define some distances which are kept invariant under Lorentz transformations. So, we want to define distances which are left Lorentz transformations. Okay. Now I know this looks a bit hazy or something essentially, but the analogy is, let us think of a simple vector in 3 dimensions, forget about 4 dimensions for the time being, for a simple second essentially. If you have 3 dimensions, say for example, and there is a vector and there is a vector r, so there is a vector r like this, okay. So, there is a vector r. Now, this vector r, okay, the Galilean transformations, now if you move it essentially, or rotations, okay, the Galilean transformations or rotations, what do they keep invariant under the transformations? Keep the length of the vector invariant, keep the length of the vector invariant, okay. So, that means if there is an r and if you apply Galilean transformations, or if you apply rotations, say for examples on this vector x y z. Okay. So, let me say that r bar is equal to x y z, and then you apply some Galilean transformations. So, this r prime, okay, x prime y prime z prime is equal to some, okay, 1 minus v t 0 0 0 1 0 0 0 1 x y z there should be a dimension full time. Okay. If you do this, this is a Galilean transformation, the distance is just changed by 1 minus v t essentially. So, this will be just a Galilean transformation. Okay. So, this is a Galilean transformation, or if you make another transformation which is like a rotation, say for example, under this transformation what happens is r bar, that mod is equal to r bar prime mod, invariant under Galilean transformations which are valid when, as long as v is much smaller than c. Now, similarly you can also ask what happens if you have r prime is equal to x prime y prime z prime is equal to a rotation matrix. You can imagine this to be some rotation matrix r x, r y, r z, and then x y z. Okay. This is nothing but r bar. So, in this case also mod r bar prime is equal to mod r bar. So, rotations. So, here I represent rotations by rotation matrices, okay, rotation transformations. You can think this as Euler angles or in various ways, rotations in 3 dimensions, these are well known. They all preserve the length of the vector. The Galilean transformations and rotations preserve the length of a vector. But what happens in special theory of relativity? The special theory of relativity, things are changed because the length of a vector is no longer a constant. In special theory of relativity, okay, and in special theory of relativity, the length of a vector is no longer a constant. It changes depending upon the frame of reference you choose essentially. So, but there should be something which is conserved, okay, there should be something which is conserved, and that is called the line element. Okay. Similarly, the time is also not conserved, time differences, time periods are not conserved in special theory of relativity, they change depending upon the frame of reference which you are measuring in. So, the time periods are not conserved, the lengths are not conserved. So, what is conserved is essentially, okay, things which are called line elements essentially, which are called line elements. So, are conserved in special theory of relativity. these are called ds square is equal to, this is defined, x square plus y square plus z square minus c square t square. This is a quantity which is conserved under Lorentz transformations, okay, because Galilean transformations are no longer valid. What is the transformations which are valid in special theory of relativity are Lorentz transformations. Under Lorentz transformations, this is the line element which is valid. But to introduce the notation, we introduce something called d s square is equal to x mu x mu. Let us first use the notation c is equal to 1, h cross is equal to 1, which is called natural units essentially. Okay. So, going to natural units, okay. Okay, let me just introduce you this x mu is first, then let me is equal to x mu. Now, this is what, now you go to one vector to another vector with a minus sign chain essentially in the t direction. So, you have x mu is equal to this. So, x mu is equal to eta mu nu x nu. So, if there is a one upper index and one lower index, that means that you sum over all the indices attaining here. So, this is like in tensor analysis, okay, this is like a tensor. So, this is called metric tensor. So, if you have one index on the top, one index on the bottom, okay, you sum over those elements essentially, you sum over that. So, to tell you what it is, x mu here, okay, x mu is equal to eta mu nu is a tensor. So, now you can choose, there are two choices 1 0 0 0 minus 1 0 0 0 0 0 0 0 minus 1 x y z t, that is equal to, okay, sorry this is not correct, okay, minus t, or you can put it in the way you put in the minus sign. So, okay, let me write it neatly in a better way. Minus 1 t x y z, that is equal to minus t x y z. Okay. So, this x mu is equal to this. So, this is your capital X mu, and this is your metric tensor eta mu nu. So, this is called the metric tensor. So, what now in this language, now what you will see is that you will get back, if you put C t here, okay, you will get back ds square is equal to x mu dx square is equal to x mu. So, this is the first notation which you have seen, the line element essentially, okay, in special theory of relativity, and for the first time you are using Einstein notation. There are other choices of metric tensor which you can use, in which you put 1 minus 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 also, that is also possible. Okay. I will come to that just after the break. Okay. I will stop now.